In chapter 23, we are talking about comparing two means. So often we want to know whether one group is different from another. For example, I want to know, do women jump higher than men, say? So I have two separate groups I want to compare. I want to see how high women jump, and I want to see how high men jump, and I want to see whether they're significantly different from one another. So doing that, we can look to see if the two means are different or equivalently. If they're different, then when I subtract them, the mean should be notably different from 0. So our calculations for dealing with two means, we need the standard deviation. So our standard deviation for looking at the difference between two means would be y1 minus y2 standard deviation would be the square root of our population standard deviation squared divided by the first sample size plus the second standard deviation, population standard deviation squared divided by the second population size. Now, if I don't know the population standard deviation, then I need to use the standard error. So it's the same formula below here. There we go, my pen's now working. All right. It's the same formula below here, except that I'm substituting where the population standard deviation is, I'm substituting the sample standard deviation. All right, so this is now the standard deviation we're looking at when we're looking at the difference of two means. Now, let's move forward. So once I have that, then the distribution will follow a t-interval, same as what we were looking at last time, except this is the difference of two means instead of a single mean. But it's a two-sample t-interval, and we'll run a hypothesis test called the two-sample hypothesis test. It's a student's t-test again. There we go. So in order to run either the confidence interval or the hypothesis test, I do need to calculate my test statistic. Now, if you recall before, the t statistic was our mean minus the population mean over our standard error. This is the exact same formula, but now the mean is the difference of the means, and the population mean is the difference of the population means, okay? So otherwise, it's the exact same formula. So we're going to follow that when our conditions are met. So let's talk about what those conditions are. So we need to make sure that we're looking at an independent observation. So we check two things there. The randomization condition, where the data collected from using some method that is a randomization method, right? And then the other one is the 10% condition, right? We don't want to have more than 10% of the population in our sample, but really this is only an issue when the population is either very small, either very small, or if we have an extremely large sample size. Next thing that we need is we need to have a normal population. So we're going to check to see, are we roughly unimodal and symmetric? Does it look nearly normal? And then our last condition here is that our groups must be independent. So we're looking to see, now what do I mean by independent? Well, the outcome of one can't affect the other. In other words, the groups have nothing in common, no overlap where there might be some characteristics in common. For example, if I'm comparing the heights that men jump and the heights that women jump, there shouldn't be any overlap in that category between men and women, right? There's nothing that would influence between the two. Those are independent groups. Okay, so here are our conditions. We're going to be checking to make sure that it's randomized, basically normal, and that our groups are independent. If we do that, then our confidence interval is the difference between the means plus or minus the critical t-value times the standard error. This is the exact same confidence interval formula we've been using all semester. Just for us before, it was one mean plus or minus the critical value times the standard error. Okay, so now the critical value depends on the number of degrees of freedom. It's a little more complicated than what we were looking at before. In the last time when we were dealing with just one mean, our degrees of freedom formula was easy. It was just n minus 1, the sample size minus 1. Now with two sample sizes, I've got this huge, big, complicated formula. Guess what? You don't have to plug into this. All right, we're going to let our calculator tell us what the degrees of freedom are. So let's look at an example. I want to work number 16 on page 625 of the textbook. So I'm going to go over here to page 625 of the textbook. My textbook is here. And look at this problem. A researcher wanted to see whether there is significant difference in resting pulse rate for men and women. So the data that she collected is summarized here. We have 28 males, 24 females. Here are our means. They look pretty close, 72.75 and 72.625. Median, standard deviation, and so on. Okay, so we want to know, what do these box plots suggest about the differences between the male and female pulse rates? Well, if we look at these box plots, notice this shows us the mean is almost the same between the two. We saw that from the summary statistics on the previous page. So our mean is almost the same, but look at how much more spread there is in female pulse rates, right? So our means are nearly the same, but the variability is different. It's bigger for females. We want to know, is it appropriate to analyze the data using the methods of inference discussed in this chapter? Well, in order to do that, remember, we've got to check for randomization. So let's go back over to the problem statement. The data she's collected are displayed in the box below, but it doesn't say anything about how she collected the data. So we would have to say, assuming that the data was collected using a randomized technique, it looks like both of those box plots are roughly symmetric. So that nearly normal condition would be met, right? We've got just about as much over here as we do over here. So we see a symmetry on each of the separate box plots. Each one looks roughly normal from the box plots. So that nearly normal condition is met. And in the independent groups, we've got male and we've got female, and we're okay on that, right? Because we shouldn't have any influence between those two groups. So yes, part B, our answer would be it's appropriate to analyze, assuming that the data was collected randomly. All right, so now, in order to do this, we're going to go over to, I'm going to go back because we've got to create a 90% confidence interval here. I'm going to go back to those summary statistics so I can input it into my calculator. So I'm going to pull up the calculator and I'm going to hit the stat key and we're going to go over to the tests. And this time, in order to do a 2 sample t interval, I got to go down more to option one too far, or a couple too far. There we go. Option 0 here. This is the 2 sample t interval. So now we're going to choose that. This time I want to plug in the statistics, the summary statistics we have over here on the right. So our first group has a mean of 72.75. And a standard deviation of 5.37225. And the number in that sample are 28. And then our second mean is 72.625. And the standard deviation there is 7.69987. And the number in that sample is 24. We wanted a 90% confidence level. And no, it's not pooled. We're going to talk about what that means in a minute. So we're going to go ahead and hit calculate. And it gives us the confidence interval of negative 3.025 to positive 3.2753. All right, so there's our confidence interval. Now we would interpret that by saying we are 90% confident. So let's see if I can write on this. We are 90% confident the true mean difference in pulse rates between males and females is between negative 3.025 to positive 3.275. Now, what does that actually mean? That means that, because remember, we did males minus females in our test. So females may have a higher pulse rate by 3 beats per minute to males, right? Because if the subtraction is positive, then the males are bigger. If the subtraction is negative, the female's bigger. So either females might have 3 beats per minute more, or males might have 3 beats per minute more. In other words, it's not, you know, there's not a true difference. And this is what the last question here is asking. Does the confidence interval confirm our answer to part A? Yeah, the mean's about the same. How do I know that? Because 0 appeared in my interval. My interval went from negative 3 to positive 3. If 0 is inside the interval, then a true difference might not exist between the two, right? Because the true difference might be 0, meaning they might be the same. Let's look at one more example, and then we'll do hypothesis tests on the next video. So a study was done at UC Berkeley to see the effect of staring at drivers has on their behavior. So in a randomized experiment, researchers either stared or did not stare at drivers at a stop sign, and then recorded how long it took the drivers to cross the intersection. So suppose the crossing time in seconds were, here's our first group, here's our second group. We want a 95% confidence interval. Okay, so first of all, it says it's randomized. Okay, we need to check for nearly normal. So what I would do is I would graph these. Now, in order to do that, I'm going to go to the stat key and edit, and I'm going to enter the data in list 1 and the second set of data in list 2. I've already done that. If you haven't, you can pause the video here, enter the data in your calculator so you can continue with me, and then pick right back up. Okay, so picking up, once I have the data entered in list 1 and list 2, I'm going to go over to second and the stat plot key. I'm going to turn those plots to on. And I can look either at a box plot or a histogram. We looked at a box plot in the last example, so we'll just do that again. Notice it says list 1. So if I hit graph, it shows me a box plot for list 1. That looks roughly symmetric. We're okay there. Let's check out box plot for list 2. So I'm going to go back in here and I'm going to change this to second and then the list 2. And now graph. And okay, this one's a little bit more skewed, but it's not as bad. In other words, it's not perfectly symmetric, but I see the distance here is about the same. So this might fall into that category of roughly normal. I'd feel better if my sample size were higher. Okay, the more skewed, the higher it is, the more normal the distribution is going to look. Okay, So we're going to say, yeah, these are roughly normal, bearing in mind that second has a little bit of skewness. And then, of course, these would be independent because we've got one group where we're staring at them and another group where we're not. And there's no overlap between the two groups, between the drivers, anything like that. All right, so now I'm going to go into stat and over to the tests. And remember, it was option 0. And this time I want to enter the data because I have it stored in my lists. So I want list 1 as L1 and list 2 as L2 since that's where I stored the data. This time I want a 95% confidence interval, so I'm going to go down here to 0.95. Don't pool and calculate. And this time we get a 0.14 to 1.9. Now notice that in this one, 0 is not inside my interval, right? This is a positive and a positive, so it doesn't include 0. That tells me that there is a significant difference between the two groups. So one group took longer to go through. Which one? Because this is positive, it's list 1 minus list 2. That means list 1 had to have a higher mean, which I can see right here. X1 is higher. X1 was the no stare group. So without being stared at, it took the drivers longer to cross the intersection. Okay. How much longer? Well, we are 95% confident that it took them between 0.14 seconds and 1.93 seconds longer, that the true mean length of increase is somewhere inside that interval. Okay, guys, this gives you enough to work on our T intervals. We'll do hypothesis tests on the next video.